All right. So the solution, as we said in the lecture, is that the general small signal model for a three-terminal device is we could write it in this particular form. We can write it in alternative form also, as we discussed. So this is one particular form. And if we write it like this, then we have seen that the resistance is the ratio of Rn is del In by del V in here. So all you have to do is take the derivative. R0 is del I0 by del I0 by del V0. So you take the derivative there. And Gm is del I0 by del V in. You take the derivative. So directly, because I0 is not a function of V in, so you could take I in here and substitute and get it as a function of V in. So take the derivatives and put all the values and this is what you end up getting. Okay. So that's one way of writing it. The other way we said is an alternative way of writing it is we could have written it in this form of also current control, current source here. So in this case, again, the same thing. Our input resistance and all that output resistance are the same. Alpha, which we have written here when we write it, is going to be del I0 by del I. Simply ratio of that. So you can either, because it's written in terms of, you can either draw it, the equivalent circuit in this form, or you could draw it in the previous form. Okay, and get the values that we are wanting. Okay. So any questions regarding this? Any clarifications? Any questions? All right. Then let's come to the models part here. The homework problem. The first homework problem was. A two-terminal device is given. Two-terminal device is given. Its IV characteristics is given. Ix is Vx to the power 6. And because it's a very sharp nonlinearity, it's a sharp characteristics, we are saying that we could approximate it by, if we look at this one, we could approximate it by a vertical line or a constant voltage source. Okay. So the issue was, what value of that constant voltage source should we take? We know that in practice, the current is varying. The voltage is also varying, obviously, but the voltage is not varying too much. And that's why we are saying we can approximate by a constant voltage. So the issue is, what would that constant voltage V alpha be? Right? So that's what we are wanting to know. What would be an appropriate value V alpha? So how do we do this?
The current range.
What? This is the current range given. Within that current range, we have to approximate it by V alpha.
So using that formula, the IA.
Vx to the power 6, yeah?
So then I got the voltage range.
Voltage at what point?
At those points.
At 2 points. Okay, so all right then. Okay.
Then I average both of them.
Then you took the average of the two and approximate. Huh?
It's a main question. What is the weights for that average?
Weights, you're saying one should take a weighted average.
Yes, and I don't know what the weight should be.
Okay, so let's see what he did. So this is what I did also as a very simple solution. So what we are saying is we are approximating it by a vertical line. That's what a constant voltage source means. So for 10 milliampere current, the Vx turns out to be 0.46. And for 100 milliamperes, it comes out to be 0.681. And the average value is 0.572. That's one way of approximating it. And we can calculate. See, what is the overall goal? The goal is to minimize errors, right? If we are making an approximation, and the approximation should not result in very large errors. If I approximate it in this way, at one extreme, I find that the correct value is 0.464, but I'm taking 0.572, the error is minus 23.38%. At the other extreme is 0.681, and I'm taking 0.572, so the error is 15.93. So now, are there other ways of approximating? The answer is yes. See, you can see that this is sort of creating an imbalance. There's more error. So one could balance the error. So maybe if I shift 0.572 to a little higher or lower, you could do that, yeah. So the point that I'm trying to raise, there is no unique answer here, obviously. You can approximate it in many different ways. I'm not looking for a single answer. But when you have an answer, look at what the errors are involved and think about, are there other ways of approximating which may minimize the error here. Somebody suggested a integral Another possibility is we know that 0.5572 is giving rise to a larger error on the lower side. So maybe we reduce this a little bit. The next part was part B of this particular problem was a battery of 5 volt is in series with a resistor of 100 ohm and the element X. Determine the approximate value for the maximum percentage error in current when the above model is used. Okay, so note that error would increase as supply voltage gets closer to the value alpha here. So what we are asking is with a 5 volt battery attached to a resistor R 100 ohms and with an element X, I'm approximating this element X now by that simple 0.572 voltage source, and we are asking how much is the error involved in using the approximate value. So we just simply write I equal to 5 minus Vx by R, delta I is minus here, delta I by I, and so on and so forth, and delta I by I maximum is 2.4% error. 2.4% error here. Okay, so note that even though the approximation in X was fairly large, approximation in X was fairly large in the sense was resulting in much larger error, the impact on current is not that large, right? The impact on current, percentage change in current or percentage error in current is not that large, 2.4%. And the reason is because I have a large supply here. Even if I make small errors in the calculation of whatever is the voltage across X, it's not resulting in very large errors. On the other hand, you can clearly see that if this 5 volt were to go to 1 volt here, then the error would become larger here. And you can see why we are discussing this, because we are discussing this because if you recall, your PN junction diode has a large exponential characteristics, and PN junction diode we also approximated by a battery. Many times you've taken a battery as 0.7 volt here. So what we are trying to emphasize that that's an approximation, and this particular part is telling you that approximation by a constant battery would be good if the attached in series with it the power supply is large. If it is large, then the errors would be small. But if this, now imagine if this 5 volt were to get to 0.8 volt, now the errors would blow up. You can see here 0.8 minus 0.572, the errors would become very large. So my approximation that I'm making will work very well if the DC source attached with it is large, but will not work very well once the DC source that is there with it becomes small. Then the approximation becomes very poor. And then I can't approximate it by a constant voltage source. The other thing is, you see, we got this value of 0.572 over a particular current range when I'm looking at 10 milliamperes to 100 milliamperes. Next, we are saying recalculate from 1 microamperes to 10 microamperes. If the current range of interest to me is 1 microamperes to 10 microamperes, if that's the range in which I'm working with my device, then in that range, we approximate it by 0.123. Average value is 0.123 because at 1 microampere range is 0.1 and the 10 microampere range is 0.147, and so the average is 0.123. So very important point is here that when you are taking a device and you are approximating it by a certain model, now we often forget that the model that we are making is valid over a certain range. The range of validity is very important. The earlier 0.572 model, a constant voltage of 0.572, was valid over 10 milliamperes to 100 milliamperes. That's the range. Now the other model is valid over 1 microamperes to 10 microampere range here. So range is important. Same way we often forget when we take a diode and we approximate it by 0.7. Now remember that 0.7 volt approximation is valid over a certain range. If I go to a different current range, the diode has to be approximated by a different value of voltage. So these are all approximations, and the approximations would depend on what range of current you choose here. Okay, so note that how different these are. 0.572 is an approximation for element X, and 0.123 is an approximation for element X. Both are valid, but for different current range. This one, 0.123, will not work over this current range, and 0.572 will not work over this current range. Okay, so oftentimes we get a number and we forget how we derived it, or what current range we derived it, and we keep on using it at places where it's not really valid. Okay, so while you're using a model, please remember how did it come about and what is the range of validity. Where can I apply that particular model and where I can't apply. So don't forget that a very important point. In the next case, we said, well, that's too simplistic that we approximate it by a constant voltage source. Why not approximate it by a voltage source in series with a resistor R? So we approximate it by a line like this here, a line like this here. And so we want to determine now what is V alpha and what is R alpha. Now, a line, so when I say V alpha and R, all that it is saying is you're approximating it by a linear line, right? You can approximate it again by many different ways. The line can be drawn as many different ways. I've drawn a line which passes exactly through the first 10 milliamperes and the 100 milliamperes. So obviously, when I draw a line like that, the error at this particular point would be 0, and the error at this particular point would also be 0. Okay, but the error at other points will not be 0 here. So we can easily calculate what the value of R alpha will be. This is the line that I've drawn. So whatever is the value Vx2 here minus Vx1 here, Ix2 minus Ix1 here. So we get 2.41. 2.41 is the resistor, and then we can calculate what is V alpha wherever it intersects here, x-axis. We can calculate what is this V alpha here. So we're approximating it by a line like that, and we get a value of V alpha which is 0.44. So now our model is a 0.44 battery in series with a 2.41 ohm resistor. But as I said, there are other ways of drawing the line. There's not a unique solution. What else could I do? You may say, well, pass a line somewhere in the middle, or whatever. You can think of many different ways. One very common way of, another alternative way of doing it is that you don't minimize, let's say, errors at the end. But what you do is you minimize what is called as RMS error, root mean square. So you calculate whatever is the straight line, you calculate the error at every point, and you take the square of it and you take a root of it, and it's called RMS, root mean square error. So you could now fit a straight line which minimizes the RMS error over this range. RMS error over this particular range. You could do that also. That's very popular way of doing it. Whenever you're taking a curve and you're approximating it by a straight line, you do that. The straight line is the one which minimizes the RMS error. Can you do?
That in the first question also.
You could do, try whatever is the straight line which minimizes the RMS error. Yeah, you could do that. These things are now, with hand minimizing RMS error and all that, it becomes more complicated. If you go to Excel or you go to any software which does the plotting, which will give it to you, which will give you what the RMS values are. What value of straight line will minimize the RMS error here. So, so that's the other way of doing it. Let me just show you the results that you get here. See, this is the Ix versus Vx here plot. This red line is the actual Ix versus Vx over a current range from 10 milliamperes to 100 milliamperes. The red graph, nonlinear graph. This one, the top line does what? Top line, it minimizes errors at the two extreme. The two extreme, the line that I drew earlier, minimizes error at the two extremes. This one, this line that you see here, it minimizes the square root error, RMS error here. So that I fed it into a program called Origin, and it determines, minimizes and determines the line here. So this is the line that this RMS error comes out to be. And for that, if you use that particular line, then the value of the DC source is 0.467 and the value of the resistor is 2.51, which minimizes the RMS error. Okay. So I'm not expecting you to, by hand calculate it. I'm just pointing out to you, if you do the minimize errors at the two extremes or minimize error in the middle, whichever way you want to do, all are correct solutions. There's nothing wrong, incorrect or correct here. There are different ways of doing it. So I'm pointing out two possibilities to you. One is which is rather straightforward, the first one. The second one, RMS error, is this particular line that yields me a different value, 0.467 and 2.51 here. And you can see the errors involved. I've calculated the error over this entire current range here. So this one was my earlier model. The red one was the constant voltage 0.572. You can see the error, how the error goes over the different current range here. The black one that you see here, this is my the straight line which minimizes the error at the two extremes. You can note here zero error here and zero error at this point here. That's the black one. And the blue one that you see here is the one that minimizes the RMS error. So you can see the blue one obviously looks, if you look at the peak errors, it looks small, better there. Okay, RMS error here. All right. So the whole point in all of this is that we have a nonlinear curve. We don't want to use the nonlinear characteristics, makes analysis difficult. So we want to approximate it by this is a better approximation, approximated by a DC source and a resistor. And how do we determine that? Well, we try to minimize the error over a range of interest. That's very important. Over a current range of interest, we try and minimize the error and obtain a straight line. And the straight line is nothing but represented by a battery and a resistor. Okay, so that's this part here. The other one was taking the same element X. So this was, if you have to do a DC calculation. Now the other one says determine the small signal model for element X when it is biased at a voltage of 0.5. Show that the small signal voltage across X has to be less than or equal to 21 millivolt for error in the small signal current to be less than or equal to 5% here. So small signal model, if you recall, for any two-terminal element, we said is a resistor. It's simply a resistor. Resistor whose value is given by del Ix by del Vx. 1 over del Ix by del Vx. Now note, small signal models are always determined at a bias point. They're always determined at a bias point. You already have a DC current flowing, and around the DC value, you're saying I make small changes in my voltage, and what are the small changes in current, and you're looking for the relationship. So this is 0.5 volt we've already given you, that across the element X, there is 0.5 volt. And therefore, you determine the value of the small signal resistance, you take the derivative, you get Vx5, Vx is given to you, you get Rx equal to 5.33 volts. So your element X under small signal approximation is a resistor here. But note that the small signal is an approximation. The real incremental model that we said, the way you derive an incremental model is you change Vx by a small amount, small Vx here. The current I changes by a certain amount Ix here. The incremental model is this one here. This is the real incremental model. There's no approximation involved. But after this, we make a small signal approximation, we linearize it. So binomial expansion 6Vx we get here, we ignore all higher order terms, and that's what we get this one. Right? So we approximate it by this particular term. Obviously, there's an error involved in approximation. So we want to know that how much is the error involved. So error in the current Ix is what this expression predicts. Ix dash is what this approximate expression predicts. We look at the error here. We look at the error, percentage error here. And when we put 21 millivolt here into this Vx here, and Vx is equal to 0.5 here, we get 10% error. So we verify that if we use Vx as large as 21 millivolt, then I'll get error of 10%. So if you're looking for error less than 10%, then the small Vx has to be less than 21 millivolt. If you want to do calculations accurate to 10%, then you have to look at Vx less than 21 millivolt. But of course, the value of Vx that you see here, 21 millivolt, it all depends on the bias point. If I change the bias point, things may change. Okay? Yeah.
Vx values that we calculated in the first one.
First part, yeah, in this one here. Question number one, yeah.
So, is that the bias voltage that we're supposed to use?
Yeah, that's the bias voltage. But this is a independent problem. Right now, I've just told you what is the bias voltage across the element X. I've not related it to the externally applied voltage. Okay. So yes, first you do I think somewhere, yeah. So if you look at this particular part here, so normally a problem would be of this kind. Normally a problem would be that I have an element X and resistors and other things in my and power supply here and this one here. And our interest is in knowing, well, let's say how much is the current flowing in X due to this Vs. So we treat Vs as an incremental source. as an incremental source. And so what we do is we have to take out Vs first. We have to take out Vs first and do the analysis first without Vs. Do the analysis without Vs, which is what we have been doing by approximating X by a linear element and approximation and all that. So do the analysis without the element Vs here. Find out what the currents are, bias current. You will also get what is the net voltage across this element X. Next, if you're interested in knowing, well, what is the effect of this incremental source here, Vs? Now you do small signal analysis. You build a small signal equivalent circuit of this particular one here. You build a small signal equivalent circuit of this. So small signal equivalent circuit of a DC source is short. This resistor stays as a resistor. Element X, we just said, becomes a resistor here, 5.33 ohms, and you keep this small signal source here. So now you can calculate what the value of, you can calculate what is Vx for a given Vs. So we are saying that Vx has to be less than 21 millivolt for 10% error. So for that, Vx less than 21 millivolt, we can calculate what is the value of Vs. And it says Vs has to be less than 0.415 for Vx to be less than 21 millivolt. What this particular example is telling you is, yes, you can calculate how small a voltage should be for your model to be valid. This is what we did for element X. How small should the value be so that the small signal model is valid? We said 21 millivolt. But that's across element X. It does not say how small should the voltage Vs should be. So note that what may happen is that the element X may be a very nonlinear element, highly nonlinear. So to use a small signal approximation, you may want the voltage across X to be very, very small because you're approximating it by linear. You may say, well, the voltage across X has to be only 5 millivolt. That looks very small, okay? But that does not mean that the applied voltage has to be that small. The applied voltage you can see here. For Vx equal to less than 21 millivolt, the applied voltage is fairly large, 400 millivolt. Okay, so don't make many times the confusion comes in is, we learn that for a small signal model to be valid, the voltage across the nonlinear element has to be a certain level. For example, for a bipolar transistor, you will read that the base emitter voltage of a bipolar transistor should be less than 26 millivolt, much smaller than 26 millivolt. You will learn that later on in the course, which means that we should keep it around 5 or 6 millivolt here. But that's across the base emitter. It does not say anything about the rest of the voltages. The rest of the voltages in the circuit could be large. So when I'm saying I'm doing a small signal analysis of this particular circuit and I give you a value of Vs which is 300 millivolt, you may say, well, 300 millivolt is not small. Yeah, indeed. I mean, it's not small, 300, but 300 millivolt will result in an effective voltage across my element X. That is small enough to apply a small signal model. So please keep in mind, what is it that we are calling a small signal? The voltage across the nonlinear term has to be small enough for me to approximate it as a linear element. I'm not talking about the rest of the voltages and currents in the circuit. They may be large. I don't care. The only thing that I have to do is this voltage across this, I have to keep it small. That's all. Okay, so that's what we are trying to say here. So we figured out that this has to be less than 21 millivolts. So we are saying for that, Vs has to be less than 0.415. Okay. Now, it depends on the nature of the problem here. Suppose instead of 100 ohms, I had put 1K. Then, if I had put 1K here, then the whole thing would have come out to be 4 volt maybe. If I had put here 1K here instead of 100 ohm resistor, the whole thing would have come. I could have applied Vs as large as 4 volt here. Very large voltage, 4 volt. If I had put 10K here, I could have applied 40 volt here. Approximately 40 volt here because it's going to increase. Note that Rx is much smaller than 100. So this would have increased. Okay, Vs would have increased proportionately. Okay, so the applied voltage can be fairly large. All you have to do is ensure that the voltage across my element is small enough to keep the errors under control. Okay. All right. So this is the next one is an interesting problem. throughout this particular course, and in fact, in most textbooks and everywhere you find small signal approximation is thought of, or incremental circuit analysis is thought of as something where you change a voltage by a certain amount and you look at what is the change in current and change in voltage and all that. This particular problem is telling you is incremental circuit analysis, small signal analysis is very general. I need not just change some voltage or current. I can change a component. For example, in this case, we are saying there's a circuit which is given here. There's a voltage, 2 volt, and there are other voltages also there. So there is current flowing in this particular circuit. And then we are asking, suppose I change this element R1 by 10%. I change the value of R1 by 10%. I increase this value by 10%. You can see that it's a pertinent question. Why? Because let's say I may take this particular circuit, analyze it, and I find V0 has a certain value. Now in the lab, when you use a resistor, you know that when you use a resistor 1 kilo ohm, is it precisely 1 kilo ohm? What is the last band that tells you? Tolerance, right? So when you have tolerance of 5% or 10%, what does it tell you? That instead of 1K, you may get 1.1K if it's a 10%. Or instead of 1K, you may get 0.9K if it's a 10% tolerance. You may get that value here. So I may want to know that, well, what if this value increases by 10%? How much will be the change in my output voltage? I may be interested in knowing that 10% variation, how much will it result in? So there are various places where you want to know that if I change a component, if I take a transistor and suppose I change its beta by a small amount, by 10% or 20%, what would happen to my current? Will it deviate too much? Or will it still be under the range which I consider as a normal range, let's say? So there are questions like that also which are of importance. Where instead of changing some voltage or current in the circuit, I change the value of the component itself. And what we are saying is you can do that analysis using small signal approach again. Same thing is valid here. So note that what we are saying is you've already analyzed this particular circuit. And we are changing the value of R1 by a certain amount. So let's focus on this particular resistor here. The voltage across this particular resistor is VR1 initially. The voltage across this is VR1. The current is IR and the resistor value is R1. Now we change R1 by a small amount, which is shown over here, small amount R1 here. As a result of change in R1, what would happen is all voltages and currents in the circuit in principle may change. In some case, change may be small. In some case, it may be even zero. But in principle, as a general, everywhere voltages and currents would change. So we said, well, as a response to R1, let's say the current IR flowing through it changes by small IR1. And similarly, the voltage across it changes by small VR1. Now, what is a small signal model? Small signal model is a relationship between the small quantities, the changes. So from here, we can get this particular one. VR1 is IR1 times R1 plus IR times R1. Ignoring the higher order terms. There would be a term where there would be a product of R1. You can see here, if I expand this, there would be a term where I'll have a term IR1 times R1. It's a product of two small quantities. So in the first order approximation, when you take two small quantities, you know that quantity is small. So as a first order approximation, we neglect that. IR1 into R1. There's nothing telling you that you have to do it. You can include it also. But as a first order approximation, we say the changes are small. So the product of two small changes is negligible. We ignore that. So my VR1, it turns out to be like this here. So my model of a resistor, this resistor, whose value I've changed, it looks like this here. And therefore, I can represent the first term. What does it represent? VR1 is IR1 into R1. It's simply a resistor. The second term is a constant term. The second term, if you look at, this is a DC current that is already flowing in my resistor here, IR. And this is the change in this one. This is constant. And so the constant term I represent by a battery. So when I take a resistor and I change its value by a small amount, under small signal approximation, that resistor becomes a resistor in series with a battery. Because note that this is the small signal model here. Small signal model of that particular element here. And this is what we have to do. For all other cases where I'm not changing, it stays the same. A resistor stays a resistor. A battery would become short. So all this will become short. So my final small signal equivalent circuit becomes like this, where the battery has been replaced by a short. This resistor R1 has been replaced by this model here. Everything else, R2, R3, R4 remain the same. Battery again becomes a short. R5, R6, everything else remains the same. And we get this small signal equivalent circuit. And now this is the value. This is this particular voltage here. So we put here. And now we can calculate what is the small signal output voltage. So all we have to do is solve this particular one. You can solve it in many different ways. You can solve it and show that the value that comes out to be is 8.33 millivolt. So it's a linear circuit. It's a circuit given here, and you can solve this and obtain what is the value of V naught as a result of change in that value of resistor R. The change in finally the output voltage changes by 8.33 millivolt. Now we have made, remember we made an approximation. The approximation was higher order term we neglected. So let me show you the exact result. So I'll talk later on about circuit simulators in the class. So for example, this is a result obtained from circuit simulation. So we have the same circuit here. And then the next case resistor R1 was changed to 2.2K by 10% increase. And we looked at the exact value 0.5 here and the exact value here. And the incremental change in the output voltage was 7.9 millivolt, which is close to what we predict, 8.33. It's all small signal analysis is always an approximate analysis. Okay, it's an approximate answer that you're getting, but it's not far. This is 8.33 millivolt, and the voltage there is 7.9. Okay, here also is minus, by the way. This is 0.492. So. Here. Okay, so the point is the small signal analysis you can also do not just with the due to an extra source in the circuit, but you can also do to find out what if a component value changes. Yeah.
So how do we decide the polarity of this battery? Where positive and where negative?
You look at this one, IR1. How would you represent this particular term? By taking the direction of the current like this here.
So from where it goes this way, that would be positive.
Yeah. So we decide that the direction which you take a direction, current is flowing like this, and take that direction and then build it accordingly. Okay. But note that VR1 for us could be, when I say 10%, VR1 could be positive or negative also. Because VR1, the change in R1 could be plus 10%, it could be minus 10% also. Right? It could be either way. The last problem is a three-terminal device. Three-terminal device whose characteristics is given here. From I0 to V0 here. And so that's the output characteristics. I0 versus Vin is given here. And In versus Vin is given. Okay. So the characteristics are given, and we are asking that build a small signal model of the device. Again, so whenever somebody says build a small signal model of the device, the first question should be around what bias point. So we've given you a bias point. Vin is 1.5 volt. So the device is biased at a DC value of 1.5. And for two cases, one is V0 is 0.1 and the other is V0 is 2. Two bias points are given. So when V0 is 2, you can see here you are somewhere here in this region. And V0 is 0.1, you are somewhere in this region here, in this particular part here. So is there any issue in building a small signal model? We just said what does it involve? A resistor at the input and at the output a current source. So basically it involves this one here, GMV in R0. And how do we determine R0? We take this derivative. Derivative is nothing but the slope of the graph. So it's exactly the same thing, except that you have to take the slope of the graph here, slope of the graph here, and all that. So you should be able to build the small signal model of this particular element here. Okay. Any other question?